Hello everyone, my name is Ilse-M-Sustain and I'm a PhD student and I'm going to talk about my PhD project that is optimal design of integrated thermal energy conversion system for sustainable energy and desalinated water production. I will start my talk with a short introduction. In this part, I will talk about the motivation of this research, then a general vision about the renewable energy versus conventional ones, then the design challenges, the sequence of solution employed, and a case study for the optimization of the proposed model. Also, I will talk in a general way about the model and the optimization technique. Finally, some comments and remarks about the project and the phase in which the project is located. Okay, the exponential growth of the world population has led to high increases in the demand of energy and water that are increasing to meet the needs. Both are two of the most important problems in the last decade. On the other hand, the high requirements include dependence on fossil fuels, which translate into large amounts of greenhouse gases. In the same way, water scarcity forced the exploration of new technologies to produce fresh water. With respect to the water, the problem of the water in Mexico, there are areas with a little availability of water, and this is due to the climatic condition that is a low rainfall in some areas and the population growth. In addition to this, agriculture is the sector with the highest water requirements, which is why the exploitation of aquifer is increasing, and with this, the scarcity of water is a fact. The obvious problem of water scarcity leads to develop of new technologies that are capable of generating fresh water. With this, exploring water desalination system is an attractive option. The next problem is the high dependence on fossil fuels. So where does energy come from in Mexico? Okay, 76% of the total energy produced in Mexico is from fossil fuels, such as fuel, oil, diesel, charcoal, natural gas, and that is by the generation and transformation of the energy. The behavior of the use of these fuels is interesting, and this is due to the low cost and high heating capacities. But what about the renewable energy? 24% of the total energy produced in Mexico is from these renewables. In this case, 70.29% represent the hydroelectric, the biogas, photovoltaic, wind, and geothermal renewable energy. The rest that correspond 6.83% are other clean technologies. In this way, renewables are the best able to meet demand for reliable, affordable, and environmentally responsible energy. In this way, we are proposed studying the OTEC energy system, that is Ocean Thermal Energy Conversion System. In this case, the use of ocean resources is inexhaustible, and also the ocean represents the largest natural collector of OTEC system. This system works using the temperature difference between warm surface seawater and deep cold seawater, and to produce electricity, fresh water, air conditioner, and mariculture. It works using three kinds of cycles, and that is the open cycle, closed cycle, and recycle. In this case, the open cycle works using the desalinated steam from the surface ocean, and can be used this cycle to generate electricity and also desalinated water with as main products. The closed cycle works using working fluid steam with a low boiling point to produce electricity. It's important to note from this cycle we just can obtain electricity. And the other cycle is the hybrid, and this is a combination from the other two. And from this cycle, we can obtain electricity and also desalinated water. But what is the OTEC potential in Mexico? In the maps, we can see the average water temperature with respect to the deep in Mexican territory. And in this zone, the maximum temperature reached is until 30 degrees, and while at 900 meters of the depth, the temperature can be reached temperatures under 5 degrees. So in this sense, this is a good location in the Pacific Ocean to develop this kind of system. The problem statement is the optimization. We are considering the open cycle. In this case, surface seawater is extracted from the surface ocean and sent to a solar collector in order to increase the temperature of the seawater before to enter in the flash evaporator. It's important to note that the flash evaporator operates under vacuum. With this, the temperature can be evaporated from 26 degrees. Here, we consider a vacuum pump to extract the non-condensable gases and operate under vacuum conditions. Then we can obtain water steam to generate electricity, and then the desalinated water steam is condensed using the deep sea water. Also, the water generated can be used for secondary uses in homes, and the cold water in the condenser increases the temperature. Here we seek to return the cold water to a reasonable depth to avoid affecting the environment or distribute or can be used this water to mariculture. On the other hand, the approach considers the maximizing the total annual cost system, considering government subsidies such as agreed credit bonds. It's important to mention that the Mexican government and financial sector authorities consider action for policy, regulation, risk mitigation, and other mechanisms to support the development of green bonds market. Also, we are considering the maximizing the social benefit, promoting the use of renewable energy. The idea is to generate a competitive market where this type of renewable energy enters, and with this can be determined the price policy for water and electricity, considering the existing market and offer the end user an attractive price for energy and water utilities. We have some design of challenges. The first one is the operation condition of the power cycle, that is temperature, pressure, entropies, enthalpies in each point of the cycle, the amount of surface and deep sea water required, the total heat transfer and the pumping, equipment sizing according to the design variables, the total annual cost of the system. Also, we need to determine the operational policy subject to an existing market. Consider carbon credits as economic subsidy for the promotion and competitiveness of this technology. And finally, determine a competitive pricing policy. As case study, we have some location in the Pacific Ocean. As we can see in this location, the maximum temperature can be reached 30 degrees in the deep sea water, under 5 degrees, and this is a good location to develop this system. The solution sequence, we have the electricity and water consumption profiles. We know the ambient conditions, the seasonal variation profiles, surface seawater temperature, deep sea water temperature. In this case, we are fixing in 5 degrees. Also, the early and seasonal solar irradiation. This is to increase the temperature before to enter in the flash evaporator. The economic parameters, equipment efficiencies, and electricity and water price. And finally, the government subsidies. Okay, the second stage consists in determining the subsidies for social development and the price policy, subject to some constraints as thermodynamic, economic, design, environmental constraints. Finally, the multi-objective approach consists in minimizing tax and maximizing social opportunity as social welfare objective. In this case, we have the profiles, irradiance profile, the temperature, seawater temperature variation, And the last two plots correspond to the electricity and water consumption. In this case, both profiles are the upper and lower bounds and existing market, and we use them as constraints to our problem. We have the mathematical model. It consists in mass and energy equations, design equations, and also constraints. In this case, the constraints are defined by the energy and mass balances associated to operation of the units, size of equipment, and water and energy demands profiles. In this case, the distribution, we have some demand from the market and can be supplied from the OTEC system or the local electricity grid. And the same case for the water. And it's important to mention that we are calculating the emissions generated by the OTEC system compared with the local electricity grid. That is we need to use this for calculate the subsidy from the government in order to mitigate the emissions. Another important thing, we can see the OTEC system use three kind of pumps, from the pumping of the warm and cold water and the vacuum pump. In this case, these pumps can be operated using electricity from the local electricity grid or from the OTEC system. If we operate from the OTEC system electricity, we don't have emissions from this technology. Okay, we have an equation from the economic assessment that consists in the estimate the operational costs, maintenance costs, and capital costs from the equipments. Also, the multi-objective approach consists in minimizing the total annual cost and then maximizing social welfare, subject to water and energy demand profiles. That is the upper and lower bound from the market, and the price that we have to constrain to lower and upper bounds from the market. The economic objective function consists in minimizing the operational, capital, and maintenance costs from the system, and the social welfare consists in maximizing the social welfare function, maximizing the demand served, and minimize the cost of the supply. The required demand is considered which can be supplied by the local and which can be supplied by OTEC, as well as the cost of each one. The same case for all the products derived from the cycle. The government subsidy is also considered in order to reduce the final cost. The final remarks. The model considers the nonlinear behavior associated with the design and operational equipment. The formulation allows to select the optimal configuration, the operation policy, and the sizing of the OTEC plant. The model aims to analyze ocean thermal energy from economic and social point of view, and considering green bonds credit as a government subsidy allows the generation of opportunities in the development of new technologies such as OTEC system. Develop energy policies to support the promotion of the green bond markets, and government subsidies allows for a reduction in energy costs for the end user. The model considers the social welfare generated from the use of this technology. And finally, the subsidies for our new and clean technologies allow for a competitiveness in the current energy market. And now, based on the proposals described, we are working on the result, and that's it. Thank you so much for your attention. Thank you.